Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell somewhere down there, and you'll get notifications for this series and a bunch of others on our channel. We're doing multivariable calculus. I'm assuming you're doing this because you like math. If you're all the way to multivariable calculus, here we go. It doesn't matter what we're doing. We're doing double and triple integrals. Everything else is going to involve that later in the course. Specifically, 2.6 is triple integrals. This lecture, we're going to do one more volume of a solid, and then we're going to start doing center mass and center of mass of solids in free space. Let's do it. Example 1, we're going to compute volume of a solid E bounded by the plane x equals 0, the plane z equals 0, the plane z plus y equals 1, and the, whatever that's going to be, a paraboloid actually, or a parabolic cylinder. If you write x equals y squared, it's going to be a square root cylinder, a parabolic cylinder, they're going to call it. This is the object we get that we're trying to find the volume of. This is our solid E. I'm going to phrase it as a type 1, so I'm going to go from z equals 0 to z equals 1 minus y. You can phrase this, and this one's actually not so bad because everything's fairly linear and you can invert in both ways. You can phrase this as all 6 different versions, so try whichever one you want and integrate this. I choose this one, type 1, and then type 1 region D, because this is what I like to stick to if I have a choice. Therefore, the volume of this object E is equal to, can you draw them again really quickly? Zing, 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 zing. No, it's harder than it looks to draw them in free space. That was pretty close. Anyways, what do we want? Not a mess like that. The volume of our object E is going to be equal to the triple integral over E of dv. And now that we've phrased that, it's going to be the integral from 0 to 1, the integral from root x to 1, the integral from 0 to 1 minus y dz dy dx, just the way that I like. And now our integrand is nice, it's a oneer. Did you throw a oneer in there? I did. This is equal to the integral from 0 to 1, the integral from root x to 1 of z, evaluated from that to that. So you're going to get 1 minus y dy dx. Now I'll take the antiderivative. This is going to give me the integral from 0 to 1 of, now we actually should be careful, this is going to give me y minus 1/2 y squared, evaluated from root x to 1 dx. Let's simplify that. That gives me the integral from 0 to 1. I put 1 in there. I'm going to get 1 minus 1/2 is 1/2 minus this guy. I put root x in there. I'm going to get root x minus 1/2 root x squared dx, which is going to give me, if I'm careful, the integral from 0 to 1 of 1/2, which is always minus x to the 1/2 plus 1/2 x dx, which is now going to give me equals 1/2 x minus, this is x to the 1/2, so we're going to get 2/3 x to the 3 over 2 plus 1/2 times 1/2 x squared, evaluated from 0 to 1, which is going to give me 1/2 minus 2/3 plus 1/4, which is 3/4 minus 2/3, which is going to give me 4 over 4, 3 over 3, which is 9 minus 8, which is 1 over 12. Let's now do our next application, which is going to be mass and center of mass of a solid. When it's a constant, what's a centroid? Finally, you get to see. When we do solids and we have a varying density and we want to know what the center of mass is, we call it the center of mass for some reason. And then physicists like to screw with that, and they say if it has a constant density, we call it the centroid. The centroid is just the center of mass when you have a constant density. It's the same but different. Just call it a center of mass. Next application, just like for the mass and center of mass of a planar lamina, now what we're going to have is a general solid E in space, and we may have, well, it's going to, I'm hoping it has a mass, and then a center of mass, therefore, and it could have a varying density this time also, and we can do the analogs of charge density and total charge over a three-dimensional object, which we'll do next time, and we'll do moments of inertia and those types of things next time as well in applications. For this time, what we're going to do is mass and center of mass. So just like in 2 dimensions, if I now have an object, which you're like, that's a planar object, just a second, one more line and it's not anymore, and then I do this guy, and then all of a sudden now it's a solid E in the 3 space. Once I have something like that, it has a varying density, so the density is not the same at any point where it is, so it has a density rho which may vary over that solid E. The mass of that now is the same thing. Mass density is defined as mass over volume in a 3 space scenario. Therefore, we want to know what mass is, so mass becomes density times volume, and then we're going to, if it's varying, we get essentially the idea that when we sum this up using Riemann sums, we're going to get that mass is the triple integral over the density function over our solid E. Then what we're going to get is moments of mass now, not about the x and y axis, and not about how hard it is to push the thing around the x-axis or the y-axis. Now what we're saying is how hard is it to push it about the coordinate planes, which will be slightly different than moments of inertia, which are going to be rotation about the x and y and z axis. This is now referencing a moment about crossing the coordinate planes. So MYZ is the x moment, the y moment, and the z moment, or however you want to phrase that. I'm not a physicist, I'm just doing the mathematics behind this. Once we compute those moments, if I'm going to do the x, I remember the x one is y and z is there, so the x is missing, that's the one we're doing, and that's x rho x. For the second one, it's xz, so then it's y rho, and then here it's xy, so we're going to multiply by z rho xyz. Then the center of mass is going to be the moments over the mass, just like we did in 2 dimensions, except there's going to be 3 of them now. Let's do an example of that. Let's find the center of mass of this wedge of cheese, basically, is what we're going to be doing. So it's bounded by the paraboloid x equals y squared, or the parabolic cylinder, technically. Z equals 0, x equals 1, and x equals z. This is x equals z. This is z equals 0, the xy plane. This is the plane x equals 1, and then this is our x equals y squared business. The way that I'm going to phrase that is type 1 region E, because I like to. That means z goes from 2 functions of x and y, which are fairly reasonable this time. And then I've, for convenience, written this just so I didn't have to invert. Well, we could have in this case, technically. But I'm phrasing this as a type 2 region D, so y goes from -1 to 1, and x is going from y squared to 1. The reason I choose to do that is if we do it the other way, you're going to have a function of x and a function of x in both bounds. This way, at least I have constant, constant, constant. 3 out of the 4 bounds are constant this way, and that's why I pick it. And if I had done the other way, only 2 out of the 4 would have had a constant. The other ones would have had root x and a negative root x, so this is why we're going to phrase it this way. That tells me that the mass, first of all, and constant density means that rho of x, y, z is just going to be rho. That's going to give me, the mass is going to be the triple integral over our region E of rho dv, which is by properties of triple and double integrals. This is rho times the triple integral, which is now phrased this way, is -1 to 1, the integral from y squared to 1, the integral from 0 to x, dz, dx, dy. Computing that now, this is equal to rho times, I get z, I evaluate from 0 to x, which is just going to give me x, so that's going to give me the integral from -1 to 1, the integral from y squared to 1 of x dx dy. That is going to give me rho times the integral from -1 to 1 of 1/2 x squared evaluated from y squared to 1 dy. When they're more complicated, don't skip them. Maybe at first don't skip them ever. Equals rho times the integral from -1 to 1 of 1/2, and then I'm going to get 1 minus y squared squared dy. That gives me rho over 2 times 2, the integral. This is an even function. I'm checking. I should say it out loud, but my brain just internally, Pavlovianly checked. It's an even function, so I can double that up. Why would I compute those two? 0 to 1 of 1 minus y to the 4 dy, and then conveniently those 2's cancel. And I'm going to get this is equal to rho times y minus 1 over 5 y to the 5 evaluated from 0 to 1, which is going to be rho times 1 minus 1/5 which is going to be 4 rho over 5. Just 4 more triple integrals to go, or 3 more triple integrals to go, and then we've got what we need. That's the mass. Now we have to do the moments. Luckily, one of them is 0. mxz is going to be 0. Yay, let's do that one first. Or last? You should do these one last. Continuing by symmetry, what we're first going to notice is, or even though I don't prove by picture, but it's symmetric with respect to this plane. So in the with the y one, what we're going to get is mxz is 0 by symmetry. Then what we're going to notice is that we've already calculated the mass. That's half of the information we need. We now need myz and mxy, and then we can find the center of mass of this object. For myz, this is equal to the triple integral over our region E of now, how I remember, it's the variable that's not there. So this should be x times rho dv. Luckily our rho is constant. That's going to give me rho times the integral. Our bounds are going to be the same. The -1 to 1, the integral from y squared to 1, the integral from 0 to x of now x dz dx dy. That gives me rho times the integral from -1 to 1, the integral from y squared to 1 of, it's still x is a constant, so that's going to give me x times z evaluated from 0 to x, which is going to give me x times x squared dx dy. This is now going to give me rho times, and now this one will be a little bit crazier, so let's take care of that. That will be 1/3 x cubed evaluated from y squared to 1 dy. Luckily the 3 and the 2, oh, it's an even function again, so we can double that up. This will be rho times the integral from -1 to 1 of 1/3 times 1 minus y to the 6. When I put that in there, dy, this is an even function, so this is equal to 2 rho over 3, the integral from 0 to 1 of 1 minus y to the 6 dy, which is equal to 2 rho over 3 y minus 1 over 7 y to the 7 evaluated from 0 to 1, which is 2 rho over 3 times 6 over 7, which is the 3 will cancel in here, which gives me 4 rho over 7. Let's compute the other moment of mass and keep track of those, and then we can find the center of mass. The last moment we need is going to be the triple integral over E of z times dv. This time what we get is the bounds are the same always. This is going to be the integral from -1 to 1, the integral from y squared to 1, the integral of 0 to x now times z dz dx dy. We finally have a z in there, so we're going to have to compute that. That's going to give me the integral from -1 to 1, the integral from y squared to 1 of 1/2 z squared evaluated from 0 to this, which will give me x squared dx dy. This is going to give me the integral from -1 to 1, the integral from y squared to 1 of, or now we can actually compute that using the fundamental thermal calculus. That's going to give me 1/2 times 1/3 x cubed evaluated from y squared to 1 dy, which will give me an even function again, which is going to give me the 1 over 6 times the integral from -1 to 1 of 1 minus y to the 6 dy, which is equal to 1/3 the integral from 0 to 1 of 1 minus y to the 6 dy, which is 1/3. Where did rho go? Rho, rho, row your boat to get the center of mass. We could have made a song there. Patent pending, patent pending, patent pending. That's already, it's free domain. Rho is in there somewhere. That should be rho over 3 times, what do we get? We got y minus 1 over 7 y to the 7 evaluated from 0 to 1, which should be 6 over 7, and the 6 is going to cancel, which is 2 rho over 7. Good. Threw me off, I forgot the rho. Don't forget that. Now that we have that, we have the moments, we have the 4 pieces of information we need. Let's recap that and find the center of mass. Now we have all 4 pieces of information. We use symmetry when necessary. If you calculate that one, unfortunately, yes, you can do that and you'll get 0. There's nothing wrong with that. You just could have done it by doing physics argument by saying this. By symmetry, It's much easier, physicists. What does this say for the center of mass? We have x bar, y bar, z bar is equal to, now, oh no, which one's missing? So it has to be m, y, z over m, x, z over m, and m, x, y over m should be the correct values. The ones that are missing in the spot that it is what I do. If you're in the X spot, it should be YZ. If you're in the Y spot, it should be XZ. If you're in the Z spot, it should be XY. That's how I remember it. And then equals, because it's physics notation. It's terrible. What do we have now? Technically, I have over M. 1 over M is 5 over 4 rho, please. So I'm going to do that, and then we're going to put this in there. So I get MY. MYZ is 4 rho over 7 times 5 over 4 rho. Oh, nice and nicey. Cancel. Those ones cancel. In the next one, I'm going to get 0 because this one was 0. So, okay, good. And then in this one, I'm going to get 2 rho over 7 times 5 over 4 rho. Cancel, cancel, cancel. 2 cancel, which is going to give me, what did we get? 5 over 7, 0. 5 over 14. This is our center of mass of this object, which says it's going to be this balanced that direction, and then the other two we're going to have slightly different variations of where the center of mass occurs in that solid region. Please subscribe right here, hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. I'll see you next time.